So I think we'll get started. Hello everyone, I'm Michael, I'm from Antmicro, and I'm going to be talking about a new methodology tool system that we're building. It's had various names, but we kind of call it Visual System Designer, and we're going to be showing you some interesting stuff about generating code, generating like system descriptions out of diagrams, and with some interesting connections to Zephyr and other things. So I wanted to start with the observation that if you're building real systems out there in the field, supporting real product families and kind of complicated configurations of products and multi-node systems, this really changes your perspective on development. It's very much different from building something on a dev kit. And so if you really want to build things like space satellites or cars, you run into a whole set of new problems that you wouldn't really encounter if you were just doing work with a dev kit. So that change of perspective kind of gets you to think about things a little bit differently. And of course, some of the problems you might encounter, and in fact, we can see that not from a user perspective, but from a vendor perspective. If you have a silicon vendor that has 100 dev kits or 500 dev kits for their own silicon, they'll see that in order to work efficiently with this kind of complexity, there's a lot of configurations you have to take into account. There's variability, there's different variants of boards. Throughout the life cycle of your product, your BOM might actually change. So you call something board XYZ, but over time, board XYZ actually becomes a different board because you have to use different components because some of those have gone out of use and so on. And of course, at that scale, you're probably not working alone. You're working in a big team. There's many folks. There's many people geographically disjoined. There's perhaps several companies collaborating. So how do you really tackle this? This is, of course, a very big and important problem. And there's no one solution, but I think there's, of course, a very kind of obvious solution that I'll kind of talk about in a second. And complicating things further is the fact that we have a hardware landscape that's already pretty complicated, but in fact, you want it to get more complicated. You want to see more silicon, more chips, more modules, more boards being published, and in fact, we're very happy that this is happening. I think we're seeing a renaissance of new silicon being pushed out by everyone: ST, Analog Devices, NXP, Texas Instruments, and everyone's building new types of silicon, higher and higher end, more diversity. The product portfolios are getting more complex with people offering ARM Cortex-M, ARM Cortex-A, RISC-V, it's a growing market too. So overall, this landscape is really complex, and it's even growing, right? So the problem's kind of getting worse, in a sense. This is exciting, of course. Like we want more hardware. As people who work with hardware, we want more of it. But at the same time, of course, picking the right thing and making it work in an ecosystem of your products might be pretty challenging this way. So in fact, the answer is obvious. We're here at EOSS, and you can tackle this with open source. You can kind of make sure that by collaboration, even though the complexity is growing, you're kind of staying in front of a charge. You're staying kind of capable of managing that complexity. But to do that, you need some tools. Of course, one of the things that I'll be talking about today is Zephyr, because Zephyr is a very good answer to this complexity. Zephyr has had this baked in from the very beginning. It is based on configuration. It is based on a methodology that allows you to work with systems in a structured way. It doesn't just throw a bunch of code at you. There's configurations, there's device trees, there's a lot of depth in Zephyr that will allow you to build your products in a much more structured way. And in fact, with the hardware model 2 that has just been introduced, this gets even better, because hardware model 2 tries to address this problem of complex hardware, like hardware with 2 SoCs on it. How do you represent that? And I think it's a step in the right direction. It's of course not everything, and still there's a lot of work in terms of figuring out how to make Zephyr work for advanced hardware with multiple cores and so on. And not everything's fully perfectly standardized yet, but it is really going in the right direction, and Zephyr has been pretty incredible in finding a community-based solution to the problem. It's not a single vendor's idea that's driving this forward. It is a collaboration of a variety of different people. It's, of course, the silicon vendors themselves to a large extent, but it's also different kinds of companies that build products or deliver services. Everyone just tries to figure out a way that serves their own purpose, but by combining those purposes, you can find pretty good solutions. And the hardware model version 2 has actually been a pretty good idea. So here you can, of course, see some advanced NXP device with some multi-core capabilities, some Cortex-A, Cortex-M. You could run Zephyr on either of these, of course, or you could run Linux plus Zephyr. So kind of representing this properly and making it easy for people to actually do that is a challenge. By the way, the migration itself is a nice example of a collaboration. There's been a lot of course, hard work and discussions and delays and so on. But generally speaking, for example, you could see that people actually collaborated across the board, right? So you didn't just have everyone taking care of their own things, to some extent, yes, but you also had people helping each other out. You had Nordic actually kind of spending a lot of time and work to get other people's silicon across the board just to make hardware model 2 happen, right? So that's a pretty incredible way to collaborate around describing hardware, where yes, everyone has the responsibility for their own stuff, but if someone really wants to make something happen, they can also help other people to make it happen. And in fact, it does happen in practice, that you get this kind of collaboration, even between companies that nominally compete, right? So I think Zephyr enables this kind of awesome collaboration, even between competitors. And we are also developing a tool called Renode, which gives you the ability to simulate systems. Now, to simulate systems efficiently, of course, you have to model them. That's something you can't avoid. So you have the device. You normally write a driver to make your SPI peripheral run. On the other side, you'll have to build a model, and that model will have to describe what this SPI peripheral is doing. So there's non-negligible work involved in doing that. Having said this, there's a lot of great stuff that comes to your rescue. And it's the same as in Zephyr. You have a driver that might be addressing a certain peripheral. If that certain peripheral is present in a number of different boards that are related, what Zephyr does is it takes configuration, it addresses this via device trees, and you just instantiate the same driver, perhaps on a different address, perhaps with some configuration options. But generally speaking, you reuse code all across the board in a very strict and efficient and configurable manner, so that you don't duplicate code all the time. So if you're building a BSP for a different board that happens to be similar to another board, has the same SoC or a similar SoC from a similar family, you'll probably just mostly tweak configuration files. Renode does the same. So if you have models for certain peripherals in a SoC, if another SoC uses the same kind of stuff internally, then getting it to work in Renode is going to be very easy. So yeah, our simulator is kind of course, an open source tool itself, but it also benefits from other tools that are open source. And one of the things that we built is called Zephyr Dashboard, which essentially takes all of Zephyr, takes all of the 600-something Zephyr platforms, and runs, compiles binaries for those platforms in the standard way. Zephyr makes it very easy to kind of just compile a binary across 600 different boards. And then what you do is you run it against Renode, where you just generate the configuration for Renode dynamically from device trees. We have a tool called device tree to REPL that just takes the device tree, generates the Renode description. And you just kind of run one against the other, and you hope for the best. In fact, you don't have to hope for the best. There's 470 targets that we support. So in fact, we cover like 75% of all of Zephyr. And naturally, that does not mean we cover the entire silicon space, with all the peripherals and everything. We can run basic demos on 470 boards, and there is a lot of complexity involved in actually supporting all of them perfectly. But there's a great starting point for very, very many boards in simulations. You can just, in fact, this is a public website, it's a public CI where you can just go grab the binaries, you can take a look at the outcomes. And there's a lot of data that we can generate this way, because Zephyr makes this data available in a sense. We transform it, we build it, we run it, we generate traces, we generate a lot of information on top of this, and all of it is open source and then free for everyone to use. And it's a great example of how those tools can reinforce each other, where configurability, if it's baked into both of them, it gets very easy to integrate them. So this is one way that we can kind of handle this complexity. So of course, here we're testing across a range of different devices, different dev kits. But what you might do in your product would rather be you take a lot of different configurations of the same product, you take a lot of different use cases, and you run that in a massive CI. You run a lot of corner cases, you try to figure out what's breaking, what's working. Commit after commit after commit. So this runs after every commit of Zephyr, right? And we have data for Zephyr, like how is the performance of Renode versus Zephyr kind of improving or getting worse. There's a lot of demos and different kinds of scenarios that we have here, including AI and Rust apps, and so on and so on. So it gives you a lot of insight into Zephyr. Now, interestingly, of course, I'm saying about this interoperability of different tools. And in fact, we've seen this in practice already, where because we're running this dashboard, because we're building those tools, we are finding inconsistencies. We're seeing that, well, yeah, this is great, but it could be better if we did it a little bit differently, if we encoded our device trees a little bit differently, or we updated those strings here, our data would be cleaner, nicer, more relevant. And so we go and contribute those changes back to Zephyr. So you will see us making those random pull requests every now and then, just fixing random things in device trees. And if you wonder why we're doing this, well, we're doing this because of that. And this is fun because, of course, you discover inconsistencies, and you guys are engineers, you know how it works. If you find an inconsistency, someone's wrong on the internet, it's always fun to fix something, even if it's a tiny thing. So, you can see how, working with one open source tool actually gets you on a pathway to fixing other open source tools, because it's to your benefit. It's not even that you're a nice person, it's just that it happens to benefit you to fix other people's stuff. And much like in the previous example that I mentioned with the hardware model itself, people just help each other because it's good for them to do so. Now, so summing up this part, in the real world, this kind of structure that I talked about, this kind of single source of truth approach that I'll call it, is not just a useful thing, it's essential. At a certain scale, like we couldn't ever build the Zephyr dashboard, by hand or by some clever hand-generated stuff. We would have to really spend a lot of time to do that, and we couldn't maintain that. Instead, we rely a lot on automation and the data being correct. So we just have to find ways to work differently. We have to find ways which don't involve engineers spending time on tweaking little things here and there. It has to be scalable. So we use the device tree as a kind of common data model, and that feeds both Zephyr and Renode, and we make sure that those are correct, because both our Zephyr work and our Renode work needs this. So we've gone on a quest to find consistency and structure in the hardware landscape. And that quest has, I think, been going on for 3 years now. So it's a kind of a massive endeavor on our end, where we actually did a number of things in sequence. I told you about the Zephyr dashboard. But based on top of this, when we saw, okay, we have so much data, we have so many boards that we can run, we thought that, okay, we could perhaps take this data and present it in a different way. So we built a tool called Renodepedia, which is an encyclopedia of hardware. And that Renodepedia is, showing you those demos that we run in the CI in a more visual way, with traces, with everything. It was a fun experience and very useful. We still use it ourselves as a reference, and our clients do too. So Renodepedia was a great step forward. But then we felt that, okay, there's more we can do, and we also built something called the Open Hardware Portal. We do a lot of hardware, and open hardware is something that we engage in very, very much. Of course, we build proprietary hardware for our customers, but when we have reference designs, when we have kind of ideas for new boards and so on, we will, of course, try to make them open source when we can. So we have like dozens of open source designs, and we thought we needed a home for them, so we built this hardware portal. We call it Open Hardware Portal, which both hosts an open source component library that we're building. So all of these boards are built in KiCad, and we're using Blender to visualize them, and then our component library is also open source with Blender models and everything. And we just host it through a portal. And again, we're kind of looking at the landscape of devices and chips. We're like trying to see patterns, trying to categorize them, trying to make sure that we can display them in a one nice and cohesive way. And then the third thing we did was on the top. It's a tool we call Visual System Designer. So it's been around for a little while, but it actually right now is kind of growing up to be a real tool. So last year we kind of made it, and we kind of made it in a way that you can describe a system visually. Now we're actually kind of combining it with the other efforts. And we're building a system that allows you to visually represent your embedded devices and to do some fun stuff with them. And by fun stuff, I mean serious work, not just kind of demos. So like all of these things have been a very good learning experience because all of them required us to work with data and clean up the data and figure out ways to parse, the massive amounts of data. Like to put this into perspective, Zephyr has those 600 boards. We have thousands of components in our hardware database. In every SoC, there's many peripherals. If you count them all together, again, it becomes like hundreds or thousands perhaps, because there's like hundreds of SoCs, thousands of IPs in those SoCs. So overall, it's a massive scale. And figuring that out has been a really challenging thing, but also very rewarding. And we haven't only focused on Zephyr. So over time, we realized that, yeah, Zephyr is a great starting point. It's a very tidy and nice operating system with a lot of data in it. But of course, if you want to go and target the entire ecosystem, you need to also use U-Boot and Linux, and perhaps some data from vendors, and perhaps platform I/O. There's different places on the internet where you can find structured information about hardware. The challenge is in pulling this data together and actually making it sensible. But we're trying to kind of make that work. So what we're essentially building right now is a system to describe and manage entire multi-device systems you're building. So I'm giving an example here of an open source hardware setup that we're building. This is a GPU cluster that consists of mechanics and a bunch of boards and a PSU to power it and so on. And all of these can be represented in this tool. And for kind of every piece, you can drill down, go into the actual components, see what's there, and see what software is running there, and so on. So this is a pretty massive, of course, piece of hardware. But you could do this on different scales. Like, of course, it doesn't have to be a GPU cluster. It could be a smartwatch. It could be any kind of device that you're running, a medical device, a satellite that I showed before. The importance is in the connections. Like you create a connected database of whatever goes into your device. And in fact, all of this is based on open source data. Like we have, this database of components. We have the Zephyr data, and we are looking for a way. We're building a way to expose that data in a nicer way. You remember Renodepedia? This is kind of similar, but much broader in its kind of ambition. We're trying to present this data in a way where you can search things and kind of explore what kind of SoCs are there on the market, what kind of cores they are inside, what kind of I/O they have, and so on. And the interrelations between those elements are very important for us. As a slight detour, if you look at different kinds of devices on the market, for example, you will find that there's an Ethernet controller, for example, that you find on a RISC-V board, the PolarFire SoC. The same Ethernet will be found on, for example, a Atmel Cortex M7. And the same peripheral is going to be found on an UltraScale Plus, which is a Cortex-A device from AMD Xilinx. So a very broad range of hardware can actually share common components. And it's not very visible normally until you start working with this data and until you realize that there's so much IP reuse going on between the silicon vendors. There's so much structure in this. So it's kind of interesting to work with. And one of the things we want to enable is like, when you're kind of making choices, like, what SoC am I going to try to use and so on, you can filter by cores, I/O, and just make your design decisions this way. And of course, like before in Renodepedia, you can have those demos that we have a CI that builds demos for all these boards that we have Zephyr running on, and then those demos, you can just look at them, you can look at the results, you can reproduce them fully. This is all like open data, so you can get into any of these data demo, and there's just both Zephyr and U-Boot now. So you can grab the relevant binaries, you can look at the UART logs, you could look at the trace outputs, and it's a great starting point, right? Because if you took a dev board, you could basically grab a binary from here and just run it, and it should work. We actually do it ourselves. We kind of use this resource ourselves internally when we want to get started quickly. But existing boards are kind of boring, right? Like you actually want to build things that are new. So I'll get there. So we, for example, develop hardware for our customers, for ourselves. And for this hardware, we typically have some more data. Like we have data about their design. And we can, for all those open boards, we can actually generate 3D renders. We can actually generate like hot areas where you click on a component, you go to that component. And then you can also generate data about the stack up of the board. You can preview the schematics online. There's a lot of depth there that you can explore. And of course, we don't need all this data. Like if you're missing some of this data, then you just don't get some of the features. But if you have this data, and very often we don't actually need the actual design data for most of these things. It's enough for like production Gerbers and placement files. So this is pretty cool. And one of the other things that you can do if you have this ability to describe a system in a coherent way, you can generate software bombs, you can generate hardware bombs. And of course, our software bombs is something that Zephyr does, so we're kind of leveraging the capability of Zephyr. Hardware bombs is actually something that's being standardized now in a HBOM work group that's led by Kate Stewart. So kudos to her and leading that group, where as soon as a standard emerges for doing this, because we don't have a consistent standard out there for telling people what just hardware looks like, as soon as one emerges and we're helping define it, we can actually use this information to generate whatever you need, right? Because we know what the system is built from, we have all the components and so on. So now getting to the visual system designer itself, if you want to represent that kind of structure, of course you can just write it in a file, right? But we felt that there has to be a better way, or at least another way that you can augment your work. And we came up with this diagramming-based solution where you have a diagram that basically describes the connections. It's not a schematic, right? It is a block diagram, so it operates on the level of I/O, like SPI, like I2C, like PCI Express, or connectors that you connect physically. So this actually presents this GPU cluster. So there's 8 different GPU units and the main board. It's a pretty nice structure because, of course, it's very logical. You just want to run 8 GPUs together and coordinate between them. So you can describe your device this way, and that gives you a lot of interesting capabilities. So of course, it gets interesting, especially as you take different elements that are active, right? If you take SoCs, if you take sensors, if you take actuators, you can turn them into boards where you run software. And then, of course, it's kind of funny when you're building a new board, the delta T between conceptualizing the board and getting something working can be very long. You both have to develop the hardware, and then once you have the hardware, you still have to develop the software. And it might be a while before you see any result. And we want to change that, right? And we want to change that not just for dev boards, we want to change that for any kind of custom boards. So in fact, what we do is based on the structured device tree data that Zephyr has, we parse that, we kind of analyze that, and we can generate board files, device trees, and test binaries. And when you do that, you realize that, oh, I could actually have a test binary for anything. Of course, having some assumptions in place and so on, but generally speaking, Zephyr is very flexible in explaining how things should be connected. So with some clever heuristics, you can get very good coverage of different kinds of systems. And we can generate binaries for quite a lot of different SoCs connected to different sensors, and it just works. And when I say it just works, it's because you can then take those binaries and you can actually run them in simulation. Because as you remember, if we have the device tree, we can also generate a simulation file. So you put those two together, you get a full feedback loop. And with that, I will actually transition to a demo. I hope that works with this screen setup that I have now. But I did want to kind of show you how this would work in practice. I just need to fire up something in my terminal, or I'll start with the system itself. So yeah, let's see how that works. It's going to be fun clicking things on this other screen, but I'll take my chances. Or will I? Yeah, that was the wrong button. So, yeah, it's very dark here. All right, I think I got it. That's the full screen button. Okay, so this is the system itself. It's unfortunately very bright in here, so I hope you can see something. Basically, we have all those levels I talked about, right? This is a web page that pulls it all together. Of course, you have the device level, and then you have the GPU cluster. Right here. You see the GPU cluster. It has all those things in it. And you click one of the boards, you kind of get into that particular board. Because we have the 3D assets here, we can actually flip it. So it flips. It's an actual animation we generate out of Blender. This one is not very interesting because it has no active components on it. But if we go to boards, for all of these boards, of course, we have some Zephyr demos, but there's one that I have a special demo for, and this is this entire flow. So this is an environmental sensor we built with an ST chip on it, and some sensors, of course. And for this one, we have a block diagram that we created. And our aim is to actually generate those diagrams automatically as well for all of the Zephyr boards. But for this one, we kind of drew it by hand. And this diagram is special in that it isn't just a drawing, right? It isn't something that you just look at and think, oh, my system is very nice. Let me look at it. You can click Edit this diagram here. Again, sorry for the lack of visibility. And you will open an editable version of this, right? So you can take those components there on the left-hand side. You have like displays, I/O, sensors, you name it. And you can connect them up together. And those connections are actually meaningful. So, you know, this is not just randomly connecting things in Draw.io or in Google Draw. This is connecting things with the understanding that a GPIO can only be connected to a GPIO and so on. So there's a specification driving this that dictates what components are available and what things can be connected to each other. And so we have this diagram, and it's looking pretty nice, but let's do something fun with it. So let me just run the backend here. The backend will be running on my computer, but you could, of course, run it in the cloud. And now we can actually press the play button. And you can see that I pressed play, and we have a backend that just builds the Zephyr application. And I didn't have any board files or anything else on my computer for this before. So I only have the diagram, and I don't have knowledge of how Zephyr works. And from that diagram, I generate the device tree and board file. Of course, then the binary compiles, and once it gets compiled, it should start simulating. Let me see. I can't see very well on the screen. OK, so starting simulation. And I'll have to close the terminal just to show you. But here we have an LED that's blinking. And this is the real binary running in simulation in Renode. And this binary actually connects back up to Renode, back up to the front end. And we have the LED really blinking. And there's some temperature sensors getting temperature readings. You can see the UART output here. So there's Zephyr console. We see the LED state. We see 20 degrees being represented here. And we could actually, I'll try to be a little bit kind of creative here. So yeah, problem with my setup here is that I don't see it very far into this. I'll actually move this a little bit closer to me. I can do that. It's interactive. And there you have a temperature, right? So we can just edit this, and perhaps I don't know how much. OK, let's make it 1. So hopefully, I made it 1 degree. No, I made it 19, I think. OK, so anyway, yeah, I just took it down a notch. So now we have 19 degrees. We started with 20, now we have 19, and so on and so on. You can actually go and modify the diagram. So of course, you'll have to stop the simulation for that. So I will kind of go and stop the simulation by kind of clicking here. And now I can grab an LED. Let's take this one. And this LED, it has a GPIO connection. I can move it to the other side here. And I grab the GPIO connection. Sorry, this is overlapping here. So let's grab the GPIO connection. I can only connect to GPIOs. The only green ones are here, are the GPIOs here. Oh, okay. And now, I hope it works. So now I have another LED, right? Let's regenerate that. It'll take a while, of course. Let me just try. Okay, yeah, here we go. So if we minimize this, you'll see that both of the, come on. Okay, you know what? It's very hard to click here. Yeah, okay. So both of those LEDs are blinking now. And this is being regenerated live, right? So you can, of course, like take away sensors, add sensors, change stuff as you wish. So that's the demo. Of course, like there's much more depth here. You can explore the database and so on. But I think hopefully it kind of visualizes to you how it's all connected and how it's relevant. And in fact, one of the things you have to understand is that we can also do this for multi-node systems. We can do this for complex systems that run multiple binaries on them. Out of necessity, the demo isn't much more complicated than this, but you could just scale it up to more boards. You could connect boards over CAN, or, and all of that is supported in Renode. And the major challenge that we're facing is, how do we represent this graphically, right? We can make it happen on the command line, and we're trying to give people a tool that will also allow them to do this graphically. So I'll close this now, and I'll try to return to my slides, which I managed to do, I think. And so you can actually hear more about the specifics, the details of how it works in another session that comes right after mine, which is going to be showing this, but not in the context of an STM board, but in the context of a pretty complex multi-core FPGA-enabled device. My colleague will be kind of getting into the details of how that works and why are we doing it for FPGA-based RISC-V devices and so on. So you can see that if you're interested. About future plans, and that'll be kind of very quickly to wrap up. First of all, we need to release this publicly. So the system that we're building is kind of very new, so it hasn't been released. It will be released in the next few weeks, and in fact, the entire flow is open source, right? So if you want to reproduce that, there's a link here. It's not very visible, but you'll get the presentation later, and you can reproduce this. And the portal itself, the tool that we're showing here, is going to be released and public. So it's just a matter of a few weeks, I guess. We also want to have like user profiles where we can kind of save data and have private projects and templates and stuff like that to enable people to not only just work with generic boards or perhaps play around and finish and go home, but more like persist their data and try to build real systems. And of course, we'll be using it internally too, ourselves, to build our customer projects. And generally speaking, we want to enable you to like express your system and then get our help to build it, right? Either on the hardware side or software side, perhaps build simulation, perhaps build Zephyr or like an over-the-air update system. Like the sky's the limit. We want to make sure that you can represent your system properly so that once we know what it's comprised of, it gets easier to discuss what can be done with it. And with that, I'll leave some minutes for questions. Thank you very much.
So thanks for doing that. This is super interesting, especially from a sort of a lens of CI and continuous builds, and that alone makes it worth it. But so because it's cross-platform in software, cross-platform in hardware, what's the complexity behind the scenes? How brittle is this right now, or can I pick it up and run with it today?
That's a very good question. And we don't really know how brittle it is because we haven't tested it so thoroughly as we'd like. I think that if you just took it and run with it today, you'd definitely run into rough edges. This is mostly because when we parse the device tree data and so on, there's still a lot of inconsistency and things to figure out. There's no unsolvable problems there, though. Like, we don't believe this fundamentally should be brittle long term. It's a matter of it being new and kind of us building it up as we go and being excited about it. Of course, we try to present it at an early stage, right? So definitely I wouldn't recommend it to you. I mean, grab the repo, try it out for yourself, but don't use it for a production system yet, right? We will be actually the party that starts using it for the production systems, just so that we can kind of continue sharing this methodology with others as soon as we know it's safe to use it without our supervision. So I guess definitely there's some brittleness, I'm sure, but most of it is just we're parsing data with Python most of the time and generating things. And the better the source data becomes, the less brittle our algorithms become. And typically it's a lot of just string parsing really, and device tree compatible strings. They used to be kind of here and there, but they're much more precise today. The hardware model version 2 is helping, so it's all converging in the right direction. But as for is it production ready? Probably not. But we'll be the first to tell you when it's, okay, it's production ready, you should do it. Right now, our focus is release this portal so that people can actually, because you can experience it from a command line today, but that's not as much, that's not as awesome as we'd like, right? What we want here is, you fire up the portal, you wire up Renode to the portal by just running a command line, command. It's pretty simple. And then you can play around with different things. And only then you actually expose all the interesting things you could do, which are kind of the same that you could do with a command line, but it's just that the portal aspect, the exploration aspect, gives it a whole new dimension. And I think, of course, uncovers a whole new can of worms and set of problems, but that's good. We want to solve those problems.
One follow-up. You also mentioned that because of the common IP blocks used across many different parts, you can sort of get a bigger bang for buck. I work in custom silicon. How would I go about plugging my IP block into this system?
That is an excellent question. So in fact, one of the other goals that I didn't dare to mention is silicon development. So we work with open source tooling for silicon development, open source IP, and generally we do help silicon companies build chips. And we do want this to be integrated into the portal. We just chose, we pick our battles, right? So boards and systems are kind of a different use case, similar because it's all, again, interconnected and so on. So we have the encyclopedic aspect of IPs and SoCs and so on. We don't yet have the design capability where you go into a SoC. And I mean, we have it internally, right? We have a proof of concept. We have a lot of work in that field. But how do we plug it back into this publicly available system is just a lot of work. But we definitely want to do it. We're involved in things like Calypso Root of Trust. We're involved in OpenTitan, OpenSecura. We're involved in a bunch of open silicon projects, which come with a lot of open source IP. And of course, there's also proprietary IP that's very interesting that you can kind of put those both together and perhaps build a chip out of this. So we definitely want to enable that use case. It's just not going to be the first on the roadmap. But it kind of depends who's asking as well, because if we have people that say, oh, this is awesome, we totally have to enable this use case today, we're flexible to doing that. It's just a matter of picking your battles and gauging the interest. Where do we see the most people getting excited? And then probably this work will go whatever direction we see is being useful. Of course, some of it is just driven by our own projects. So if we have a lot of product development projects, then perhaps the product development side of things will develop faster. Versus if we have a lot of silicon projects going on, suddenly you'll see features popping up related to silicon design, because we kind of tend to build tools that we use ourselves. Renode originated, for example, as an internal tool that we only open sourced after a few years when we realized it's useful in a broader context. So you will see a lot of our stuff when it's popping, when you see some open source releases from Antmicro, it's typically a customer that's driving them, or at least a use case that targets a group of customers.
Thank you.
Some more questions? No? One question from my part. So you're generating device tree. So I guess that it means that you're generating all the pin control, clocks, and so on, clock configuration, and so on. Yes.
Yeah. Yep. Of course, and I think there's quite a lot of work to be done in that space, especially. So we'd of course generate some default values, and how do you actually make it easy to graphically configure stuff like pin control is one challenge that we have to tackle. So good point. And Right now, we would just generate, whatever is the default. But I assume there's, some things that people might want to tweak in that regard. And we've already talked about that. We already have plans how to do it. It's just a matter of implementing this.
Okay. Thanks. No question? Okay. So thank you. Thank you, Michael.